This machine is like a giant instrument, a new telescope to an astronomer. Instead of using it to search for new cosmological discoveries, we're using it to explore the relationship between mathematics and physics.
It's a very multidisciplinary science. We have physicists, which are probably the most common people who work on quantum computing, but we also have somebody who's in applied mathematics.
If you look at reality one way, you see physics. You look at it the other way, you see mathematics, and it's actually both.
We're in that same kind of moment in time where we're looking at the first or second transistor here. There's a revolution taking place, and it's kind of exciting to watch it play out.
It represents a way that humans can expand the knowledge that they have and the problems that they're able to solve.
It's a game changer for the corporation, it's a game changer for our customers, and ultimately it's a game changer for humanity. Computationally, this is the equivalent of the Wright brothers at Kitty Hawk. Quantum information science, quantum computing certainly has the potential to be a turning point in history. This machine is the first practical step that will essentially reset us on Moore's curve.
Moore's law is an observation that the number of transistors on a chip doubles over a certain time period, or the cost of the transistors halves.
But we now know today that there is a limit to how small you can shrink things, how many transistors you can cram onto a single chip.
So that's going to bound human capability for tackling certain problems. This machine offers an alternative.
And this might be considered the rebirth, maybe, of analog computing for solving certain kinds of problems.
Optimization is searching for the best possible answer among a large set of answers.
These are the kinds of problems that cannot be solved by calculations with classical digital computers.
For example, it would take many times the age of the universe to try to identify the folded state of a protein. And yet nature can do this in seconds or maybe minutes. It's had billions of years to think about it. We're trying to solve similar kinds of optimization problems.
It mimics nature to find the minimum or the maximum of a design space.
If we can simulate 20 years of evolution in 10 nanoseconds, then we could evolve our engineering systems to be much more successful than what they are now, and it would cost very little. If we actually tried to do that in reality, the cost would be horrendous, and the amount of time it would take would be intolerable.
The most important thing to remember about ordinary computers is that they work with bits, which can be either 0 or 1. In quantum computing, the fundamental unit of information is not a classical bit of 0 or 1, rather it's a qubit, a quantum bit, which can be in a superposition.
Superposition means that the system is in some mixture of the 1 state and the 0 state.
And as a result of that, when you have a string of these quantum bits, you get a multitude of possibilities. So if you have 2 quantum bits, you have 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1. Those all coexist. And a quantum computer can parallel process all these possibilities.
The idea of a quantum computer is that you build it based on quantum physics, the physics of the very small, rather than classical physics, which is the physics of the large world we see around us. When you get down to smaller scales, things become probabilistic, things interact with different physical effects than the ones we can see on a large scale, or those physical effects manifest themselves in different ways. Quantum computers exploit these probabilistic phenomena in a way that makes a new kind of problem solving possible.
Let's say you're climbing mountains and you're looking for the deepest valley in this mountainous landscape.
Probably what you will do is begin to walk downhill, and you will continue to walk downhill until you start to walk back uphill. You'll say, I went through the minimum, and you'll turn back around until you find that one point where you're not moving up or down, but you're just stationary. And you can think of ground state as being that lowest possible energy state.
In quantum mechanics, we're allowed to perform something called tunneling. We can literally go through walls.
With this particular machine, it's based on a simulation of this thermodynamic process that includes quantum mechanical effects that allows it to continue to explore the space around that valley without actually climbing up and over and being restarted, but to essentially tunnel through the mountain and find out if there is actually a lower valley on the other side. And it will continue to do that until it reaches the ultimate lowest valley.
It's always an interesting one to explain to a layperson because it's one of the really weird things that happens with quantum mechanics. And the fact that you have weird things happening in quantum mechanics is because you can exploit these effects that you don't have in your toolbox when you have a classical computer.
There are a lot of problems that are provably very hard, NP-complete or NP-hard in the jargon.
And you want to use the shortest path possible, or you want to route things in a way so that they all arrive simultaneously. So you're looking for an optimization in terms of time management or resource allocation or minimizing path lengths.
Of course, people have been trying to solve them with clever heuristics for half a century.
Using a quantum computer, we would hope to be able to develop algorithms that allow some improvement in the calculations of these problems.
It allows us to consider problems that prior to today have been beyond the scope of anything that we thought was possible.
Problems of energy, healthcare, transportation. The list of problems that we're all familiar with, those can all be eventually solved.
The idea of having hardware that can essentially drive straight to the solution, perhaps better than our clever heuristics, is really attractive.
It's our mandate, it's a moral, ethical requirement that we look at applying those capabilities to where they will do the most good in the future.